Okay, so this one's going to be about, it's a stream of consciousness on what I'm working on or looking at in physics. And I just watched this video about splines. And while I was watching this, they're talking about continuity, parametric continuity, I guess it's called, and what they call geometric continuity. I've never really looked into splines very much, but so we look at continuity relative to with respect to the derivatives, the first derivative, the second derivative, etc. And that's I guess the parametric continuity. And, also the position, I suppose. That's the C0 continuity, the first one. The fact that the curve is actually connected. Okay, or I guess that the control points of these splines are connected, whatever. And while I was looking at the continuity stuff, I kept wondering if this person, Freya Holmar, was going to go into complex numbers and what's it called? Holomorphic functions. And I kind of wasn't expecting them to because it seems like a little bit of an overload. I don't know if they've looked into it themselves. I'm sure people have. Actually, I found a paper that I think might have to do with it. And it's called, if you just search splines holomorphic, it's a paper called Convergence of a Class of Interpolatory Splines for Holomorphic Functions. So maybe these splines, what I was picturing while I was looking at these splines is sort of bigger vector fields, right? This is only about 2D splines, so 2D vector fields. And then I think that if you restrict yourself to a certain kind of those, you're looking at basically complex functions. And if we talk about the complex functions that are differentiable everywhere, continuous and differentiable everywhere, those are called with fancy language holomorphic. And it seems that if it's once differentiable, then it's infinitely differentiable, it seems, in the complex case. And so that's interesting. So, but it's sort of a small region of such a holomorphic function tells you everything about the function everywhere. It sort of fixes everything in place. And I think that one way to study these is just to look at Mobius transformations. Let's see here. Change the color. Font. Mobius transformations. Maybe make that a bit bigger, huh? Yay. Which I'm not going to go into here. But these are... I'm not going to go into it. There's a geometric way of looking at this and a 2x2 complex matrix way of looking into it. And it's isomorphic to SU2. And I'm interested in the idea that there's a lot of things, but there might be some connection to the fact that you only need one derivative. So, first of all, I'm thinking of these things sort of more generalized. I'd like to look at not just complex functions, but quaternionic functions and vector fields in 3D space. And so I think there's an analog here, but I suspect because I've never really seen information about it, maybe I just didn't look or something. Maybe it's right there, but I've never seen anything about a higher dimensional analog of Mobius transformations going to, say, the quaternionic case. I think there's a reason for that I'll get into. So I'm looking at so if you're talking about three-dimensional vector fields, well, immediately you might think of electromagnetism, all the laws of electromagnetism. We can kind of package those, I'm pretty sure, into quaternionic algebra or into Clifford algebra. And so what was I going to say? So I think that there's a difference when you go to 3 dimensions, that things can kind of get knotted up a bit. And I have sort of pictures in my mind or things that I pretend I can imagine about it, but where's the pencil now? Oh, okay. So if you look at something like the Hopf vibrations, there's lots of fancy visual things, and this is kind of what these fancy visuals are kind of what I'm picturing of vector fields that they kind of get knotted up in some way, which you don't have in the complex case. And I'm imagining singularities, which you can have in the complex case, and that the space between it, for example, everything has to be continuous, but let's say you had some kind of path going from one quaternionic singularity to another, that this path in 3D can kind of be spun around and then sort of it can be spun around a finite number of times and sort of knotted up, and then we can form some kind of geometry where we connect these two singularities, and so this represents, if we go from one singularity to another along some path, it represents a quaternion where you're moving from one quaternion to another. So we're talking about functions of quaternions. And I'm being hand wavy here, but if you have like a initial quaternion and then a sort of destination quaternion, basically, so you only need 2 quaternions to form an octonion. You can have some quaternion. Look into how octonions can be constructed. I think you can have some kind of other quaternion like that to form octonions. And so I'm thinking of these sort of transformations where there's sort of paths. I don't know if transformation is the right word, but all of space is sort of having this vector field over it, and you have paths which are basically transformations from one initial quaternion to a destination quaternion, which we can just kind of package in an octonion, because you can take 2 quaternions and package into an octonion. It's similar to how you only need 2 generators to generate a quaternion. You don't need 3. We usually think of it as IJK, but you only need 2 generators. So if you have 2 generators and then you add a 3rd generator, you get the octonions. I should say if you have 2 complex generators and then you add a 3rd one. So it's kind of what I'm interested in, and I think that this can kind of get knotted up, and space itself can kind of get twisted into knots. And if you look at knot theory, you learn that something that is of interest is really not just looking at the knots themselves, but the complement of the knots, which is all of the space except for the knot. And I think that the theory of knots is really about what ways can space, 3-dimensional space, get twisted up. So I think there's some correspondence here between octonions and these transformations of quaternions, and knot theory. And I think maybe looking at these sort of 3D vector fields is kind of a way to bridge that gap. I mean, it wouldn't be surprising because knot theory is known to have to be related to quantum field theory, and octonions are known to be related to quantum field theory. So I'm not sure. So the question is about this connection. And so this represents octonions. And okay. So that's something I'm interested in. And let's see. There's I think another way to make this correspondence may have to do with symmetries in 4 dimensions, possibly the 24 cell, and which is sometimes called the hyperdiamond. But I was looking at there's a paper that seemed interesting. It's a preprint I think, called Towards a Geometric Understanding of the 4-Dimensional Point Groups. I'll say the names, I don't know if I'm pronouncing it correctly. Leith Rastanawi, and Günter Roth. So, and this, within this group, I guess, you have subgroups of polyhedral groups, which includes, it says it's related to the regular polytopes, so I believe it includes the 24 cell. And it has these other groups that it looks at, and this paper classifies this stuff. So I think that's very interesting. And it includes these Hopf vibrations as part of the symmetry. So yeah, this has got to be related to symmetries in 4 dimensions, I'm pretty sure. And the 24 cell is in there somewhere. I think that the projections of the 24 cell can be used to create these. Well, so if you had one projection of a 24 cell, let's say it's an orthographic projection, so like rays of sunlight, I think it forms a lattice of basically a honeycomb structure called the rhombic dodecahedrons. And I think so. But if you projected light from a point instead of orthographically, then I think you would get these. You could get, like, for example, singularities if the point approaches the 24 cell until it gets on the surface. When it hits the surface, you end up with these singularities. It could be on the surface from the outside or from the inside, or from the bottom or from the top. And so I'm imagining that this, so if it's an orthographic situation, you have this sort of honeycomb, and this 24 cell can be tiled in 4 dimensions. So you get this, you can, with this projection, you can get this infinite honeycomb of rhombic dodecahedrons, which is kind of meant to be flat if in the orthographic case, and then when you go to this perspective projection with a point light, it should stretch and squeeze these rhombic dodecahedrons, and that this could be used to form sort of a different way of formulating this kind of idea of a vector field where things are sort of twisted and possibly knotted up. Where I'm imagining at each point in 3D space you have for each point in 3D space you have the position of a point light that casts this projection of the 24 cell. And we vary this continuously as we move around in 3D space. So I believe that this could create sort of 3D vector fields with all kinds of singularities all over the place, which could possibly correspond to elementary particles. That's an idea that is not looked at very seriously lately, I don't think. But there's the 1935 paper by Einstein where wormholes, so-called wormholes, are introduced, or Einstein-Rosen bridges, I think is what they're called. Einstein actually talks about this. Now he dismisses it, but I don't know that his reasons were well-founded. So, if you look at ER equals EPR and this kind of stuff, it's looking to me like there's the correspondence EPR, correspondence between entanglement and wormholes, so entanglement and singularities, in other words, fermions and singularities. So I think it's an important thing to consider. And with this kind of squishing and twisting of space, I think it wouldn't be hard to sort of derive or formulate something that looks like general relativity and the singularities. I think that perhaps characteristics of these singularities and the kind of transformations that you can get when you move around this point light around the 24 cell can give you the different degrees of freedom that you need for QFT. Possibly. That's what I'm interested in. So I need to look at top vibrations and the symmetries in 4 dimensions that I was talking about, and projections of the 24 cell. Yeah, that's it. Is that it? There's some other things which are not the main thing, but of side interest. Let's see here. But I have them in my notes. Frenet frames are related to this business with vector fields and that kind of thing. Yeah, I'm going to leave it at that. Osculating circles. Also of interest. Related to paths. You have a path, quaternionic path, I guess I'll call it. And you look at osculating circles or osculating spheres connected with that path. That's it.